Alright, so today we're going to talk about maximizing, well not maximizing or minimizing, but related rates with a three-dimensional objects such as a cone. We have here a cone, and it's basically a circular pyramid. And let's assume that it has some sort of water or some sort of liquid filling it up right here. Make this my height. Okay, so let's say this cone has a radius and a height right here, and it's got some sort of liquid or fluid in it right here. So what I'm going to do is I'm going to make this new radius, and this is a new height. Sorry. And let's say that this water is leaving this cone. So let's say that the water is leaving the cone at a alright, so let's say it's leaving at 5 pi centimeters cubed per second. Okay? Alright, so what we need to know is we need to know what type of object, because obviously this is a container. So it's safe to say that this container's dimensions won't change. So let's say this is 20, and this is 8. Okay, and now we're basically ready to do some related rates here. So let's say I wanted to look at the radius. Okay, I wanted to look at the radius of this, and I wanted to say, okay, how fast is the radius changing? Because the water's falling out, therefore this circle here is getting smaller. Therefore, the radius is changing. Okay, so how am I going to find the new radius here? So I know that the amount of water leaving, which is volume, 5 pi centimeters cubed. So the change in volume, dt, of the water in the tank is negative 5 pi. Well, because it's decreasing the volume level in here. Well, I mean, if maybe it's filling something up out here, that would be increasing the volume, but right here it's decreasing the volume. So what I want to find let's say I want to my bad, let me write it down. Find the change in the radius. Alright, so dr dt is what I'm trying to find. And then we need a when, let's say we want to do this when excuse me, let me zoom out right here. Actually, let me just move over. Find the change in the radius when the tank, let's say when the height is is 6. Okay, so we want to find the change in the radius when the height is 6. Alright, so, and I just made that up because you can find the change in the radius whenever. That doesn't matter. It's just part of the, we just can solve whenever we want, or for whatever we want. So let's say the equation, all right, what equation am I going to use? I know the change in the volume. I need to find the change in the radius. Well, let's use the volume equation. So the volume is equal to 1/3 pi r squared times your height. That's the volume of a circular pyramid, or a cylindrical cone, okay, or a circular cone. All right, so here's the problem here, okay? I could do this. I could just straight up take the derivative of all this. I could just take the derivative of all that. But that would be very tough. That's first, second, and that would be a product rule, okay? First function times the second function. Also, well, you might be asking this, all right, so why can't I just plug in 6 for the height? And that way I wouldn't have to mess with the height. Well, I can't do that. I can't do that for two reasons, or for one reason. The height is changing with respect to time. So I can't treat the height like a constant. It's a function on its own. It's much more than an x that I can plug into. And it's changing. You can't plug anything in that's changing in your original function if you're planning on taking the derivative, because once you take the derivative, you need to basically take back that plug-in, because the derivative has a change in the height. Okay? So we're still left with this problem. We've got two variables, well, really three, with the volume. So let's stick to the original volume, and we're gonna get rid of this problem. Okay? We want to find the change in the radius, so why not just get rid of the height? Well, how can we get rid of the height? Let's look right here. What we have is, in this cone, is two right triangles with the same angle here and the same angle here. Basically what we have is two similar triangles, and we know that the ratios of corresponding sides of similar triangles are equal. So basically this R and this H, or sorry, this R and this H, all right, are proportional to this R and this H. Well, what does that mean? R over H, sorry. So let's make a proportion. That's what we're trying to do. All right. The small r, and it doesn't matter. It could be this R and this H, or this R and this H. They're all proportional. So this R over this H, the new R over the new H, is going to be equal to, well, what is this R over this H? Well, that's 4, and that's 20. So equal to 4 over 20. And there you have a simple proportion just using similar triangles. All right. Now this is going to allow me to get rid of R right here, because I need R. All right. So I need to know what R is. So I work, and I find out that simplifies to 1/5, and then R is equal to 1/5 times H. Multiply both sides by H. Okay. Well, now I have that. Okay. Well, I don't want to replace R, do I? I'm sorry. I want to replace H, because I want dr dt. So that's a good mistake to make, because now I know that this proportion, there's a reason I have to solve for the correct variable here. I want to solve for this one. Well, really, I could use the step R equals 1/5 H, and then I can multiply both sides by 5 and say H is equal to 5R. Okay, so now I'm ready to substitute into H. So now V is equal to 1/3, all right, pi, oh, I missed my pi right there, pi r squared and 5r. Well, great. Now I have 1/3, actually 5/3. I can move that constant over. 5/3 pi r cubed. Well, now I can take my derivative. This seems like easy street now. Okay, my bad. I was off. I was off there. Sorry about that. Alright. Now I can take my derivative, and it's the same thing that we've been doing. Alright. Same thing. We know the derivative of this is dv dt equals 5/3. I'm sorry. Yeah, well, I could do it this way. 5/3 3 pi, because of the multiplication. Alright, then you got r minus 1, so now it's r squared. Alright, and now you take the derivative of the inside, dr dt. Okay? Alright, so there you go. Now this is easily solvable. Substitute negative 5 pi. We need dv dt, and we need r. Okay, we need r, and we need dr dt. Okay, so this is interesting. I'm not just going to substitute. I'm not quite done working. So, but this negative 5 pi right here, that's what I'm going to substitute for dv dt. Okay, so let's go ahead and do that. Negative 5 pi equals that's that'll just be 5 pi. All right, r squared dr dt. Now we still need r. Well, that's interesting. Well, we can find r using one of these formula over here. Okay, well, this one right here. Well, how do I know that gives me r? Well, it's set equal to r, but I need h. I need to plug in h. Well, I am given h right up here. I'm given h, alright, when h equals 6. So now I'm circling back. I'm spiraling using information. I am just continuing to use different equations and different information. So h equals 6. So I'm going to plug that in. Okay, that's going to give me r equals 6 over 5. Okay, now that's going to give me negative 5 pi equals 5 pi. 6 over 5 squared is 36 over 25. Okay, well, I'm going to divide, now that's dr dt still. I'm going to divide this out. Okay, well, that's just going to give me negative 1. And then 36 over 25. I divided 5 pi. Alright, dr dt. Well, ran out of room there, sorry. I don't like having this thing so zoomed in, but when I zoom out it looks too small. Alright, so 36 over 25 dr dt. Okay, so now I multiply both sides by the reciprocal. 25 over 36. 25 over 36. So I have negative negative 25 over 36. Equals dr dt. And when I divide that out, let's see, when I divide that out, I get negative 0.694 repeating equals dr dt. And that means the radius is decreasing at a rate of negative 6.94 centimeters per second. Okay, so let's spiral back. Okay, and let's see. Let's zoom out. Let's see the big picture here. Okay. So I basically did my no find when in my equation, and I couldn't take my derivative. This ratio allowed me to take my derivative by replacing the h with 5r, which I did here, and then it became all this pi r cubed, and now I was able to take a derivative. Once I had my derivative, I needed a couple things. I needed dv dt and r. Well, dv dt was a given, okay? So dv dt was up here, alright? But r was not. But I just looked back through these equations to find r, and I did, and I substituted what I knew h was, and that gave me r. Okay? And now that I plugged that in right here, it was fairly easy to square it. Got 36 over 25, divide it, multiply it, and then I knew my dr dt, and you can write it as a decimal or leave it as a fraction. Alright, hope this helps with your homework. If you weren't third period only, if you weren't assigned any homework third period, which you weren't, second period you don't have to pay attention to this, but third period only. Okay, same scenario, okay, and I know my picture stinks, alright, but you have a cone that's leaking, alright, let's say at a rate of 10 meters squared per hour, okay. And what we're going to do is, let's say this is 50 meters by, and let's just say R is equal to 15 meters. And of course you have the new R, the new H of your water level. Okay. So there's the scenario, okay, and the questions are a find dr dt when r equals, let's do r equals 10, b find dr dt when h equals 10. And so that's all your homework for tonight, guys. If you're in my third period, if you're in my second period, you've already been assigned homework, so no worries. Alright, peace out, guys. Hope this helps.